So far, all the practice problems regarding air resistance have been algebraic. Let's do one that's more numerical. So let's say you're standing on the top of a 25-meter tall tower, and you take a piece of paper and you crumble it up into a ball and you drop it from rest. So it accelerates for the first several meters and eventually, rather quickly probably, reaches its terminal velocity. And let's say you have a friend down below who measures how much time it takes to fall the final 10 meters. And they find that that time is, 5 seconds. It takes 5 seconds to go the final 10 meters. Okay, and we'll say the mass of the wad of paper is about 5 grams. So the first question, what's the drag coefficient for this wadded up piece of paper? Okay, so let's solve it this way. When the piece of paper is first dropped, the free body diagram is just mg pointing down. Then it falls a little bit, and there's a little bit of resistive force bv pointing up. Ultimately, over the last 10 meters, right, for this last portion of the fall, the free body diagram during that portion is the free body diagram that represents terminal velocity. So the upward drag force and the downward pull of gravity are equal in magnitude. So we know that B times terminal velocity is equal to mg. So that means we can find B by dividing mg by the terminal velocity. Well, we can get the terminal velocity pretty easily. It travels 10 meters in a time of 5 seconds, and it does that at a steady speed. So the terminal velocity is just 2 meters per second. Let's make this problem easy and let g equal 10 meters per second squared. So the B value in this case is 5 grams, which is 5 times 10 to the negative third kilograms, times 10 meters per second squared, divided by a terminal velocity of 2 meters per second. So what does this give us? 5 times 10 to the negative 2 divided by 2. The units are kilograms seconds to the negative first. So we have a B value equal to 2.5 times 10 to the negative 2 kilogram seconds to the negative 1, or we could just call it 0.025. All right. Next question. So exactly 1 second after this person releases the ball of paper, what's the speed? What's the value of v after 1 second? Well, we can go through the whole derivation here, but basically, if we look at this free body diagram, we can make a differential equation. Say net force is equal to mg minus bv. We replace net force with ma, and we replace a with dv dt. Well, there's a few other steps, and if you haven't practiced it on your own yet, you can refer to your textbook and watch my previous lesson on how to derive the formula for velocity as a function of time from here. But the final result will be that the velocity is equal to the terminal velocity times 1 minus e to the negative b over mt. A graph of velocity versus time looks like this. It approaches this asymptotic value known as the terminal velocity. Okay, so we could use that equation to find the speed at time t equals 1 second. We just need to plug in the given values. So v equals 2 meters per second times 1 minus e to the negative 0.025 divided by 0.005, right? The b value, the drag coefficient we just found, is 0.0025, and the mass is 5 grams. So there we go. So if we let t equal 1, let's simplify this. This means v equals 2 meters per second times 1 minus e to the negative 5t. So let t equal 1, and v is equal to 2 meters per second times 1 minus e to the negative 5. That's the same thing as 2 meters per second times 1 minus 1 over e to the 5th. We'll grab a calculator and see what you get. So we find that the velocity after 1 second is 1.987 meters per second. Wow. Okay, so it's almost reached its terminal velocity in a time of 1 second, right? If we look at this graph, this asymptote right here is our 2 meter per second line, and so after 1 second, it's almost reached the terminal velocity. Okay, so maybe we can ask the third and final question and say, how much time does it take for the speed to equal 1 meter per second? So if the terminal velocity is 2 meters per second, how much time does it take? How much time does it take to reach a speed of just 1 meter per second? Okay, well, we'll just rearrange the equation. So v divided by v terminal is equal to 1 minus e to the negative 5t, or e to the negative 5t is equal to 1 minus v divided by v terminal, or negative 5t is equal to the natural log of 1 minus v divided by v terminal. So time is the natural log of 1 minus v over v terminal divided by negative 5. Now wait a minute. Does that mean we're going to get a negative value of time? Well, no, we're going to be taking the natural log of a value less than 1, which will give us a negative value. So we're going to have a negative over a negative. So we'll get a positive answer for time. In fact, what we're going to get is the natural log of 1 minus 1 over 2, right? We're saying how much time until v is equal to 1 meter per second, and we know the terminal velocity is 2 meters per second, so 1 minus 1 half is itself 1 half, and the natural log of 1 half divided by negative 5 gives us a time of about 0.14 seconds, 1400ths of a second. All right, so stand at the top of a tower, crumble up a piece of paper and drop it, and after just 1400ths of a second, the speed has reached 1 meter per second, and it won't take long until the speed is very nearly 2 meters per second. So for the final distance, the object just falls at a constant speed known as terminal velocity. All right, so there you have it, just a numerical example of how we can apply these equations regarding falling with the influence of air resistance.